Okay, so this video is going to be a super condensed version of the 1.2 notes. Alright, basically, what is a limit? This says as f of x becomes arbitrarily close to a single number L as it approaches c from either side, then the limit of f of x as x approaches c is L. Okay, what all of that means is, let me draw a picture here. We have this function, we'll just say it looks like that, and as x gets really close to this value c, so let me show you what this means. On either side, as the function is coming towards c from the left, and as the function is coming towards c from the right, x is getting, this is the x-axis, x is getting really close to c, well then the y value, or the f of x value, must also be getting close to another number. We're going to call that L. That's the limit. Now at this point, there could be a point, okay, like that. There could also be a hole, and other things can happen as well. So let's look at the rest of this. Okay, so when we're looking at limits and we're given the function and we're asked to find the limit as x approaches -1, the easiest thing to do would be to just go ahead and plug -1 in for x. So on this one we'd have 4 minus -1 cubed. That's going to equal 5 when we do the number crunching. Okay, this is called a well-behaved function because it's continuous. Continuous for right now just means no holes, no jumps in the graph where it jumps from one thing to the next, and no asymptotes. In this particular video, I'm going to go ahead and skip over continuity because this is covered in 1.4 and I'll have a better video up of 1.4. Okay, so I do want to mention this part right here. The value of the limit related to the behavior of the function, it's really important what's happening near the x value, and it has nothing to do with what's happening at the x value. So when we're talking about a limit, this is why I told you you could have a hole right there. If x, right here, where the x value is c, we still have a limit of L because the graph is doing the same thing on the left. It's approaching this location as on the right. When you're talking about a limit, it's okay that the actual point doesn't exist. Okay. There are times, though, when the limit doesn't exist. And this is going to be this graph right here. If we were to draw this, we have 1 and we have -1 on the y-axis. There's a hole on both of these, and the graph goes in different directions. And this we can call jump discontinuity. As the limit as x approaches 0 of this function, well, it's doing two different things. On the left side, the y values are really close to -1. On the right side, the y values are really close to 1. Since these are not the same, this limit does not exist. We call the left-sided limit does not equal the right. Okay, now this is an interesting question because it's the same function, but it's a different x value. So let's think about this. 1, 2, 3, 4, 5. Well, right here, if I were to extend this function, the limit would exist. So the limit only doesn't exist on the first example because there was a jump at that x value. But at x equals 5, and around that, there was no jump. It was just a standard line. And that limit would be 1. On the next example, we could actually draw this. Sorry about that. On this example, we could actually draw this piecewise function, but we don't really need to. We know we're going to have two pieces. Okay, first line of defense on any limit problem is to plug 2 in. Now we're just going to have to do it on both pieces. So when I plug 2 in on the top piece, I have 2 over 2 plus 1. Okay, that's 1 plus 1, that's 2. That's the left-sided limit. The y value is getting really close to 2 on the left side. Now on the right side, when I plug 2 in, get 3 minus x, or 3 minus 2, that equals 1. This is the right-sided limit. So again, because these two, the left and right, they don't equal each other, this limit does not exist. Another different example is when we have unbounded behavior. This picture looks about like this. There's a vertical asymptote and a horizontal asymptote right at the axes. I'm drawing them a little bit off so that you can see them. And we have a curve here and a curve here. And if you notice, the limit as x approaches 0 of 1 over x squared, what's happening really close to x equals 0 is a vertical asymptote. This is unbounded. The limit does not exist. You almost kind of want to say that the limit equals infinity, but by saying that the limit is infinity, you're saying it doesn't exist because infinity is not a number. Also, another thing to notice on this one, and I'm going to do this in a different color, is that if we were to take this and we were to plug 0 in, we'd get 1 over 0, which also implies does not exist. The next type of not existing limits is a wildly oscillating behavior. So oscillating, let me explain to you what this is. This cosine of 1 over x, by the way, is really strange. It starts going crazy in the middle, and then it levels off. So if we're trying to find the limit as x approaches 0, well, I don't know what's going on right there. It's not obvious at all. The graph is going up and down, up and down, up and down, up and down. So this limit does not exist. Now, that's only when x approaches 0. If x is approaching a number off to the side, that would be okay. All right, but for this one, the limit does not exist. Okay, so now we're going to look at some examples, and just a friendly reminder here. The limit, anytime you see limit, it doesn't necessarily matter what's happening at x equals c, or at a particular point. So on number 4, we're trying to find the limit as x approaches 2. So we look over here, right here is where the 2 is, and we don't really care what's happening at that point. That point right there is f of 2. f of 2 is negative 2. Got it. Okay, but like I said, don't care. All right? Limit, we're looking for where x is really close to 2. And I can see that the graph is narrowing down on this point, and it happens to be a hole in this problem. But it's not that the limit is always at a hole. It's just that the limit has to be on the graph. And that y value is 1, so that's your answer. The limit is equal to 1. Now over here on number 5, we're trying to find the limit as x approaches 2 of f of x. So again, I find the 2. I know that up here is the actual point. I don't really care too much about that. Although something is different is happening in this one. Okay, what's happening on the left is different than what's happening on the right. They're not converging to a single point. There's a jump here. And that does not exist. This limit does not exist. Okay, now we're looking at number 6, the limit as x approaches 0 of f of x. And so I find where x is 0, and I notice that I have oscillation. Oscillation does not exist. Be careful with this. Don't just look at oscillation and say does not exist. It's only when x is really close to 0. But that was the case here, so we're good to move on to the next problem. Okay, number 7. The limit as x approaches 1 of f of x. So we find our 1, we look at the graph right here, and this is what we call a well-behaved function. When x is 1, the y value is -1. That's your answer. Okay, now we move on to number 8. Like I said earlier, what you always want to try is to plug the value in. If it's a well-behaved function, it's as easy as plugging a 1 in, and if I can get a number as my answer, I'm good to go. But here, I get 0 over 0. What this is a hole on the graph. And I've seen from past examples that I can have a limit with a hole. The limit could exist here. All right, so what I'm going to have to do is go back and go back and factor. So this is equal to the limit as x approaches 1. And I'm not going to go over how to factor a cubic. You can easily Google that formula, and this is how you factor a cubic. Doesn't come up that often. Alright, now look, the most important thing I want you to see is that x minus 1 cancels with x minus 1. Well, that again, that's like the hole we were talking about. Now you just plug in 1 again. We removed the hole, plug in 1. So I get 1 squared plus 1 equals 3. That's my answer. Okay, number 9. You may be thinking sum of cubes now. But no, remember the first thing you always want to do, not factor, but just plug in the 1. We plug it in. If I get a number, it's a well-behaved. If I get a 0 over 0, it's a whole. Well, something different happens on this one. It's 2 over 0, okay? It's not a whole. It's a vertical asymptote. All right, so one thing to recap here is a whole was 0 over 0. Let me just draw a line here between these two problems. A whole was 0 over 0. Vertical asymptote, a number over 0. A whole has the limit. This limit was 3. Vertical asymptote, this is that unbounded behavior we saw earlier. It looks like that. So we're going to say this limit does not exist. So 0 over 0, you got to do more work to find your answer. A number over 0, there's no limit. So that's what this paragraph is talking about. 0 over 0 is called indeterminate form. It means that the limit exists, you just got to do a little bit more work. So this happens again on number 10. So when I plug in -3 into the top and the bottom, and you do all that number crunching, you get 0 over 0. This is a hole on the graph. So what I want to do is do something so that I can get rid of that hole. Well, the easiest thing we know of right now is factoring. So we're going to factor the numerator, x plus 3, x minus 2, and factor the denominator. And really, when this happens, a term should cancel out. If it doesn't, then somewhere you went wrong. And then you just plug in the -3. We removed what caused us to have 0 over 0. And so that's our answer. Number 11, again, before you factor, just plug it in. And when you plug in -5 here, you get 25 plus 15 minus 10, and on the bottom you do get 0. Okay, so we have not 0 over 0, we have 30 over 0. So just like above, this is not a hole. This is a vertical asymptote, therefore the limit doesn't exist. I'm not going to do 12 and 13. I'm going to talk more about that in class. This, though, quick lesson of 1.2 gives you all the basic information that you need to know about 1.2.